Unit 10 is all about quantifying the uncertainty that we have when we go and fit the MLE estimator to come up with the best guess for the parameter of some probability model. So we come up with a guess, but then how wrong are we? How far off are we going to be? And what I'd like to use as the motivating example is a model that tries to describe the spread of COVID-19 through a population. Now, we've looked at the COVID-19 simulator before, where we impose a fairly simple social network on a population of, in this case, 200 individuals, and we look to see how the disease spreads as time progresses. It starts out with one person initially being infected. They're connected to at least 6 other individuals in the social network, and the probability of transmission upon contact is taken to be 20%. Now, in this particular example, what we see is that the cumulative proportion of the number of people in this population that's been infected has this kind of S-shaped pattern. So it starts rising rather exponentially, but then things start to level off. And if we move to a different network design, we see the same shape materialize again and again and again, kind of this increase and then this leveling off. Here's an example where actually it didn't spread at all. It just died out with that first person. But if we change that first person, we do see this sort of telltale structure. And if you've been following along other ways to model the spread of COVID-19 through a population, very often this is just what we end up seeing. And this sort of curve, this sort of S-shaped curve, actually has a special name. It's called the logistic curve. And if we were to write an equation to describe what that curve looks like, well, one thing that we could write down would look something like this, where essentially the proportion of the individuals that have been infected on a certain day is equal to some number, kind of what it levels off to, maybe 75%, 50%, 25%, kind of the long-term fraction of the population that ends up getting infected, times this relatively complex formula that involves, a fraction. It involves e being raised up to some power. But it's a pretty powerful model that does a pretty good job of describing a lot of things in nature. So this logistic curve, actually, it's related to logistic regression. That's really the curve that we used. And any logistic curve looks like this. We have this slow but then exponential increase, kind of a turning over point where things start to level off, and eventually we get to the overall fraction of the population that ends up with the disease, 80% in this case. And just by switching up some of the parameters here, just rewriting that equation, if I were to go from 80% to 30%, we get that leveling off at 30% here. If I go back to 0.7, it's going to level off at 70%. And if I change the value of those two numbers, and that B0 and that B1 parameter here, that controls what the kind of shape of the S-shaped curve looks like. So if I change this to a minus 0.9, what we see is that kind of moves that increase a little bit earlier on. If I change that to a smaller number like 0.1, well, we'd have to change the limit here to see what that happens. It takes a lot more time for that increase to really occur. And so these two parameters are helping to describe what the shape of that S curve really looks like. And so the question becomes, we're still relatively early in the spread of COVID-19 through the United States. What is this curve eventually going to look like for us, either in Tennessee as the US as a whole? And you might think that's actually a pretty difficult problem because if we look, let's say, at some data, we don't really have access to that much of the curve. So for this data set, here's what I'm doing. So each individual point represents a single city. So on the horizontal axis, what we have is the day of the outbreak. Each of these cities, just for simplicity, I'm going to assume has exactly 1,000 people in them. And so we have 3 cities that have been part of the outbreak for 9 total days, 10 total days, 16 total days, etc. So this is just a snapshot of a bunch of different cities at one point in time. It's not representing the evolution of the number of cases in any particular city. These are all 1.1 city just kind of snapshotted after a certain number of days after the outbreak has commenced. So if we would like to fit some sort of logistic model here, what is that S-curve going to look like? If I just change the axes right here, we see that we're not really probing too much of what that curve looks like. We don't have that kind of leveled off close to zero at the early parts of the outbreak. We don't know where it's going to turn over and eventually where it's eventually going to kind of taper off. So what is this S-curve going to look like based on the data that we've collected? What's going to be the best guess for what the overall fraction of individuals that'll end up having the disease going to be? Where is this turning over point, this inflection point of this curve going to be as well? How can we use this relatively limited data to come up with a good guess of what's likely to describe the spread of this outbreak, and also how much uncertainty do we really have with that guess? Now, in Unit 9, you actually laid the groundwork of how you could approach a problem like this. If we're counting up the number out of 1,000 people that had been infected after a particular number of days, well, that's going to be a binomial distribution. That's counting up the number of successes out of n trials. And if we count an infection as a success, which is kind of a weird thing to do, then the binomial distribution is doing a great job of describing exactly this situation, counting up the number of infections out of 1,000 individuals. The only twist is that instead of that probability being a constant as the number of days progresses, we can actually write the probability as some function of the number of days after the outbreak. And so we still have a binomial model. We know n in this case is 1,000, the number of trials. Normally we've been figuring out what to measure from our data to best guess what p is, but there's a little bit of a twist that p actually has 3 unknown parameters that contributes to it. So it changes as day is progressing. A is this eventual leveling off point, the total fraction of the population that ends up with COVID-19, with this B0 and B1 kind of describing the trajectory of that S-curve on the way there to the leveling off point. So how steep it is, what is the turning over point, how many days have to proceed. And so you know enough to actually go and maximize the likelihood, basically what are going to be the right values for A, B0, and B1 that gives this model the highest chance of producing the data that's been collected. And it's a bit more advanced. This isn't something that we'll do in 471, but if you were in the graduate program, you would learn how to unlock some more powerful optimization algorithms to figure out, all right, what's the best fitting curve. But if you do this, you can actually come up with a pretty reasonable fit to the data. Let me make a plot of the data that we have so far. So no clear sign of where that leveling off point is going to be, or the eventual fraction of individuals that will have that disease. But if you use the maximum likelihood methods to come up with best guess estimates for that A, that B0, that B1 parameter that's describing how the probability is changing over time, we find a pretty good fit to the data that we have so far and a guess of what's going to happen in the future. It looks like actually, based on the data and the best fitting curve, we're kind of probing what this turning point is, this inflection point, to an eventual leveling off point. So in this case, if we actually look at the MLEs for this probability model, the MLE comes back with a suggestion that 75.5% of the population is eventually going to become infected with COVID-19. So this might be our best guess, but as business analytics practitioners, we always want to fill up or follow up with what's the uncertainty that we have with that best guess. Is this a 75% give or take 0.1 percentage points or so? So this is really nailed down. Is it plus or minus 15 percentage points? What's the amount of uncertainty that we really have? And so that's what we want to be turning our attention to with Unit 10. How close is our best guess? How close is the MLE likely to be from the truth? And can we come up with a confidence interval, a range of values for this unknown parameter that are plausible based on the data that we've collected? So putting this in a slightly different context, let's imagine that we're working for a manufacturing plant and we're manufacturing hard drives. And we'd like to know, well, based on the manufacturing process, how can we describe the time to failure of these hard drives? Hopefully you haven't been in a situation where one of your laptop hard drives or computer hard drives have just outright failed. I have been, and it really, really is terrible to basically lose any sort of access to our hard drive. That's when you really have to hope that you have a good backup. Back in the day, I didn't have great backups all the time. I actually lost the final version of my PhD dissertation. So I have a PDF of it, but if I ever wanted to go and, modify a little bit of it, work on that research, I don't have the final copy anymore. So let's imagine that we are going to use as a probability model something that takes the failure times of these hard drives to be memoryless. Essentially, the amount of additional time that it's going to take the hard drive to fail is independent of how long that hard drive has already been in operation. And we know that our continuous memoryless distribution is the exponential. So maybe this probability model is the one that we want to take. So this is the formula for the exponential distribution. The shape of it, how fast it's decaying, depends on the unknown parameter lambda. And we would like to be able to make a pretty good statement about what this value of lambda is to help sell customers on our hard drives. So not only what the best guess for lambda is, but what some uncertainty about that best guess, and how can we leverage that to come up with a 95% confidence interval for the average time to failure. So we're in this world where we think we know the probability distribution that's making the data. We just don't know what the right flavor of that distribution is. What is the best value of lambda? And so maybe we have some data here. Maybe we have data on 150 different hard drives. And here's what we end up seeing. Some hard drives failed very, very quickly after 0.014 time units. Maybe this is in weeks. The average was about 4.4 weeks until failure, and the maximum, it lasted 21.3 weeks. So maybe these are actually months or years. Whatever time unit we're working on, we have some data, and we'd like to use this data to come up with a great guess for what this lambda is. All right, well, if you go through the math, and there's some examples of how to do this on the last unit, we can come up with a pretty good guess for what that parameter is that's describing the shape of the exponential distribution just by measuring the sample average. The MLE says that if you want to come up with the value of lambda that gives the resulting exponential distribution the best chance of producing the data that you've collected here, well, calculate the sample average and get the reciprocal. So in this case, we measured the sample average to be 4.2, so taking the reciprocal, we would come up with a guess for that unknown lambda parameter of just a little over 0.22 here. So that's our guess, but how wrong do we think our guess is? We're smart enough to know that our best guess for lambda here, the MLE, probably isn't going to equal exactly what the true value of lambda is. That's kind of spitting out these failure times for these hard drives. So we want to know how wrong are we? Based on our guess, can we say, okay, it's 0.2266, give or take zero point 0.1 or so, 0.01 or so? What's the accuracy that we have with our estimate? And can we come up with a confidence interval, actually, to help come up with a range of plausible values for lambda based on the data that we've collected? And the answer to both of these questions is a resounding yes. And in fact, fitdist is really going to help us out and pretty much just do all the work for us. So when we go and do a fitdist on a set of observations, fitting it to a notorious distribution just with EXP or a custom distribution, when we get a summary of that fit, we get the MLE estimate. There's that 0.2266, basically 1 over the average of the sample values. And this second number right here is what we're going to use as our best guess for how far off our guess is. This is going to be our standard error, just like what we use for the standard error of our p-hat when we were running a Monte Carlo simulation, trying to come up with our best guess of the probability of some event occurring. And what fitdist is letting us know is that this estimate of 0.2266 for lambda is probably off from the truth by about 0.0185 or so. So we've nailed it down actually to a pretty good guess. And in fact, there's this fantastic property of the maximum likelihood estimator that once we have our best guess and also our guess for how far off or how wrong our guess is, we can come up with a 95% confidence interval immediately just by going best guess plus or minus 2 standard errors away, much like what we did when coming up with a 95% confidence interval for P when we ran a Monte Carlo simulation. So that's kind of the spoiler. There's not much that's really covered in this set of notes here. We can pretty much just summarize it as okay, if we want to put up a 95% confidence interval or a 99% confidence interval, whatever level of confidence that we have in mind, that's pretty easy to do. We just take our best guess, whatever that MLE is, and then move some number of standard errors away. The standard error we're going to read off of fitdist, and the number of standard errors we can actually get by appealing to the normal distribution. Just put in the desired level of confidence, get the relevant quantile out of the normal distribution. For 95% confidence, this Q-norm function evaluates to be just about 2, and then we can call it a day. We're going to have a range of values that are plausible for the true value of that unknown parameter based on the data that we've collected. And in fact, I've already calculated this for our COVID-19 simulation here. If this was the data that we collected, every single dot represents one city snapshotted a certain number of days after the outbreak occurred. Each of these cities have 1,000 different individuals. When we go and find the MLEs, we found that, okay, the best guess for where this levels off is at 75.5%, indicating that our best guess for the total fraction of the populations that are going to come down with COVID-19 is 75.5%. How accurate do we think that guess is? Well, in this case, this is the value of the standard error. It looks like we've nailed it down to plus or minus 10 percentage points. So a relatively large standard error in this case. If I wanted to come up with a confidence interval, well, I could take that 0.55 or 0.755 and then go plus or minus 2 standard errors away. And so based on this probability model, based on this relatively simple model for the way that we're taking the disease to be spreading through the population, I would be 95% confident that ultimately somewhere between 56% and 95% of the population for these 1,000 person cities would end up coming down with the disease. And so that's what we're struggling with right now is we're trying to get in the data phase here. What is this curve eventually going to look like based on how the disease is spreading so far? When is this turning point really going to be, and where is it going to level off? And so this is how the epidemiologists, the statisticians, the analytics practitioners are doing it. They're assuming some sort of probability model that describes how this probability is changing over time, and then it's just a simple method of employing maximum likelihood to figure out the best guess for what this curve looks like, and then figuring out where this leveling off point is. The MLE estimates tell us everything we need to know about the best guess, and then also how wrong we might actually be. So that's the main takeaways, really, from this whole unit. But there's, of course, a lot more that we can go and say about what we're trying to do here. So the first section of these notes is just a review of the key ideas from Unit 9. And you can read over these slides much like what you would do as a textbook. It kind of sets the groundwork for what's the problem we're trying to solve, how we're going to go about solving this problem. And so these slides, as you remember, since there's no great textbook for learning statistical theory, statistical methods in a business analytics context, this more or less is your textbook. And so you can read over these slides and have a pretty good narration of what we're trying to do. But just as an extremely quick review, here's the world that we're living in right now. So we're assuming that we know the probability distribution that's making our data. It's a normal distribution. It's a Poisson distribution. It's an exponential distribution, like with the failures for those hard drives. The only problem is we don't know what that unknown parameter is, that theta parameter, that's giving the distribution its shape. So we don't know what flavor of the distribution that we're working with. We want to use data to come up with the best guess possible. And we're assuming something very special about the data that we've collected, namely that we're dealing with a random sample. So every data value that we've collected is independent of one another. They're all coming from this one common distribution. We just don't know what flavor it is. We have a random sample. In other words, our sample is an IID sample from the probability generating distribution. So the rest of the slides go over, how do we go about estimating this? We have two main methods here, the methods of moments estimator that matches the formula for the average value of the PDF or PMF with the sample average to come up with a simple rule that says how we go about coming up with a guess for that unknown parameter. And then we have the maximum likelihood estimator, which is really what we're going to stick to from here on out, where we say, all right, based on our probability model, let's write out a big long equation that describes the probability of collecting the data values that we did. And then we'll go and we'll choose the value of the unknown parameter that maximizes the likelihood, gives that resulting probability model the highest chance of producing the data that we collected. And so if we do this in the general case, we get a nice simple rule for what we need to do with the data values once we've collected it to come up with that MLE estimate. And so we've said that there are, pros and cons to the methods of moments, the maximum likelihood estimator. We need to consider the bias of an estimator. How far off typically are we away from the true value? Are we systematically coming in with a value that's too high, too low, or on average are we kind of hitting it right on the head? We would prefer unbiased estimates. But there was a second side of the story that talked about the quality of an estimator. Essentially, what's the standard deviation or variance of that estimator? Do I typically come up with estimates that are fairly clustered around the average, so pretty consistent? Or might my estimate be relatively just kind of scattered around the average value? We talked about how the overall quality, the ultimate quality of an estimator, was really its mean squared error, kind of a compromise between the bias and the standard deviation of the estimator. And so we talked about why the MLE really was the one that we wanted to stick to. So we know that for large samples, the MLE is nearly unbiased. On average, it hits it right on the head. And it turns out that among unbiased estimators, the MLE just happens to be the one, and you can show this theoretically, that's going to have the lowest variance of all unbiased estimators. And so that's why we use the MLE for large samples. On average, it hits it right on the head, and of all unbiased estimators, it's going to be the one whose values are clustered the closest to the truth. And so this is what Unit 10 is all about, following up with these very big questions here. We know that our MLE theta hat here that we've calculated from the data, that's not going to be exactly equal to theta. We're going to be wrong by a certain amount. So can we quantify just how wrong we are? Ultimately, the upshot is yes, and we're going to be able to read off the number from fitdist. And then big question number 2 is, can we push this a step farther and come up with a confidence interval? Can we come up with a range of values for theta that seem plausible based on the data that we've collected? So can we say something like, we're 95% confident that theta here is between 0.23 and 0.26? Once again, the answer to this question is going to be yes, and it's surprisingly easy to do. Easy to implement, a little bit more difficult to do by hand. We don't really need to be living in the by hand world anymore, but the good news is that yes, there are answers to both of these questions, and that's what Unit 10 is all about. Very easy to implement just computationally using R. More difficult if we want to stick and do the algebra and do this all by hand, but we will, at the end of the day, be able to come up with a guess for what the standard error is of our estimator, our best guess for how wrong our estimator is, how far off theta hat is from theta, and also we'll be able to come up with a 95% confidence interval. So let's review a little bit about how we actually came up with a standard error and a confidence interval for P based on a Monte Carlo simulation, because this is very much tied into exactly what we're going to do when just talking about the general question of how do we best guess, the value of a parameter for a probability distribution and quantify how far off that guess is. The logic is going to be exactly the same. And so let's review, how did we come up with a number for our standard error? How far off our best guess is from the truth, at least how far we think it is, and how we converted that into a confidence interval. And so back in Unit 3, quite a few weeks ago, this was the world that we were living in. We were going to run a Monte Carlo simulation to estimate the probability of some event occurring. And so let's imagine that we're running a Monte Carlo simulation to estimate the probability of some stock out using a particular inventory control policy that we're interested in studying. And so what we do is say run that Monte Carlo simulation for a total of 1,000 trials, and we look to see how the fraction of trials where we saw a stockout evolves as the number of trials increases and increases. We know that in the long run, this kind of wiggly little curve here eventually settles down onto that probability, and we get closer, we get closer, we get closer to what that true probability is from the simulation that we're running. The fraction of trials where our event of interest occurs eventually settles down pretty much exactly on that value of p. So if after 1,000 of these trials we found a stockout occur in 90 of them, we know that the MLE, methods of moments, and what we did back in Unit 3 says here's what you need to estimate from the data to come up with the best guess of p. We're going to take our p hat to just be the fraction of trials where our event of interest occurred. So what fraction of trials did we have that stockout? Well, 90 or 0.09 or 9% here. So our question is, well, how wrong is this guess? We know that it's not going to be 9% exactly in the long run. It wiggles up and down above that true probability. So after 1,000 trials, how far off are we? So how did we reason through kind of our formula or our guess for what that standard error was, how wrong our estimate might be? So that was our goal in Unit 3, was to come up with a measure for the standard error of p hat. How far off is our value of p hat likely to be from p? What's this typical error that I end up making when I run a Monte Carlo simulation? And then what range of plausible values for p are consistent with the data that I've collected? So after 1,000 trials, 90 of them result in a stockout. Can I say I'm 95% confident that the stockout probability is, say, 9%, give or take, say, 2 percentage points or so? What can I say about that? So the upshot is that there is a pretty simple formula that we could use to construct both of these. There's a formula that told us what the size of the error that we typically make is after a certain number of trials of a Monte Carlo simulation end here, and it's tied into what we ended up measuring. Take the square root of p hat, 1 minus p hat, divide by n, and that was going to be our best guess for how wrong our estimate p hat was. And then we could turn that into a 95% confidence interval just by taking our best guess and moving plus or minus 2 standard errors. Then actually we discussed an even better way of coming up with the confidence interval. Binom test is a much superior way of coming up with a confidence interval that doesn't rely on any sort of guesswork or approximations. And really that's the world we should be living in when we're trying to estimate p. But these wonderful formulas that are very easy to use, still nice to have kind of our back pocket. And so where do those formulas really come from? Well, with the stockout probability problem, let's just kind of complete the analysis here. We got that 9% best guess for the stockout probability. Throwing in those numbers, 1,000 total trials, a p hat of 0.9, into the equation, we get a standard error of about 1 percentage point. So that 9% is probably off by about a percentage point or so from that true stockout probability. What's our 95% confidence interval? Well, 9% plus or minus the margin of error, 2 times that standard error. So 9%, give or take 2 percentage points. We're 95% confident that the true stockout probability, based on our simulation, is somewhere between 7% and 11%. So where did these formulas come from? Well, I want to show this plot again, not only because I think it's just really pretty. I would love to print this out and hang it up on my wall here. But the way that we stumbled upon those formulas was to sit down and say, okay, well, what would happen if we sat, say, all 1,000 Stat 201 students down and asked them to flip a coin 800 total times and to keep track of the trajectory of their personal p hats, the fraction of flips that resulted in a head so far? Well, because of the random nature of this process, each of the trajectories of these 1,000 different students is going to look a little bit different. So each of the trajectories is being color-coded to set them a little bit apart from each other. And back in Unit 3, we talked about some of the key properties that we saw with these trajectories. Number one is that as we increase the number of flips, we saw the trajectories kind of edge closer and closer and closer to the true value of the probability. If we're dealing with a fair coin, we know that each of these trajectories are eventually going to land on 50%, well, at least edge closer and closer to this horizontal line here. And we see that, as we increase the number of trials, the distance that these trajectories are away from 50% is getting closer and closer to 50% here. So as the sample size increases, we tended to be a bit more accurate in our estimates. But there was always, a certain amount of error that was involved. And it looked like that this curve here, how close we were getting, might be well described by some sort of an equation. And so our goal was to figure out, well, what is our equation for that standard error? Typically, how far off any one of these trajectories might be from that 50% line. And so what we did is to study this at a particular number of flips here. So let's imagine that we said, okay, well, let's go and look to see what happened after 200 flips for each of these 1,000 students. Let's slice this plot right here at 200 flips, and let's see what values of p hat that we measured through the simulation, what these 1,000 different p hats these students were reporting back to us. And what we saw was that if we looked at how far off the students' p hats were from the value of 50%, we actually saw a pretty recognizable shape for this distribution. So some students measured a value that was very, very close to 50%. The difference was relatively small. Other students measured a difference that was pretty far away, 5 percentage points either above, 5 percentage points maybe below. It looked like that the distribution of how far off each of these p hats might be from the truth was actually pretty well described by a normal curve. And all normal curves have a very, very special point to it. We call that the inflection point, where the curve goes from sloping down to sloping outwards. And we said that since all normal curves have this special point on it, why don't we use this location, the distance between the peak and this inflection point, as our measure of the standard error, the typical difference that we end up seeing between a p hat that's been measured from data and the true value of p. And in this case, it looks like the standard error where this inflection point occurs, the distance between the peak and that inflection point was right at about maybe 3.2 percentage points or so of the time. And so we ran with this, no matter where we sliced at 200, 400, 600, 800, 10,000 different flips, we always saw this pattern that the distribution of the possible p hats that we might measure had a predictable shape. It was well described by a normal curve, allowing us to make the comment that the typical difference between 50%, the truth, and the p hats that students eventually measure, what we eventually measure from our data, was actually well described by a normal curve overall, just with the standard error that was related to our sample size and the true value of the probability of the event that we were looking at. And so we said, well, that's a really great pattern to recognize. Let's run with that. One thing we know about the normal curve is that 68% of the values from a normal curve actually happen to be within one standard deviation of the peak. It also turns out that 95% of values from a normal curve are within 2 standard deviations of the peak. And so this allows us, kind of a reasonable way to come up with a confidence interval. If we know that 95% of the time, the p hats that we're eventually going to measure are going to be within plus or minus 2 standard errors of p, well, why don't we take that one p hat that we measured from our sample and go plus or minus 2 standard errors? We have a formula for the standard error, how wrong we think we are. Going plus or minus 2 standard errors kind of gives us a 95% chance of creating an interval that covers the true value of p. And that's how eventually we came up with our formula for that 95% confidence interval. And so the upshot is that coming up with the 95% confidence interval for p, the probability of some unknown event, was fairly straightforward. Take our sample, take our Monte Carlo simulation, measure p hat, get the value for the standard error, plus or minus 2 standard errors was our 95% confidence interval. And we had that very special interpretation of what confidence was referring to. So we knew that because p is a fixed quantity, it's a value that has a number, we just don't know what it is. It doesn't make sense to talk about the probability that p is inside a particular range of values. It either is or it isn't. We just don't know. We don't use probability to quantify things that we just aren't privy to. Instead, what's random here, what we talk about the probability of actually occurring, is the procedure that our p hat plus or minus 2 standard errors actually does produce a range of intervals that covers the true value of p. And we've seen this slide before. If we were to go and ask each of these 1,000 different Stat 201 students, based on their value of p hat, construct a confidence interval for p, Some of those students' confidence intervals are going to get it just right. This first one does, the second one does, this third one does, etc. In this case, these simulations are trying to set up to estimate an event that has a probability of 30% exactly. So whenever that 30% falls inside that confidence interval got it right. But not all the students end up with confidence intervals that do get it right. Some miss it where p is outside the range. All of the red confidence intervals here miss 30% from being covered inside. And so this is what that confidence was referring to. We're never really going to know if any one particular confidence interval that we construct is getting it right and covering the true value of p. That 95% confident just means that in the long run, about 95% of the time, our procedure is coming up with an interval that covers p. In other words, in the long run, about 95% of 95% confidence intervals include p. So, wouldn't it be nice if the MLE had similar properties? We only measure one MLE from our sample, our theta hat here, but what if the distribution of the theta hats that we might measure when we go and collect data has a similar property as to what we saw with the p hat? What if we find something that says the distribution of the possible p-hats that we might measure is well described by a normal distribution? Well, if so, we're going to be able to employ the same logic once again to come up with a 95% confidence interval. We would just have to figure out, well, what's that standard error? What's the distance between the true value of theta and what we might measure from the sample? And so that's what we're going to pursue. Now, before really sitting down and really diving deep into the properties of the MLE, what we might measure from a sample, I want to go and actually revisit this whole problem of estimating p from a slightly different angle. I want to actually look at the likelihood function itself and see what we can learn about how far off our best guess might be from actually just studying the likelihood function. So back to this motivating example, we're trying to estimate the probability of a stockout. We've run a Monte Carlo simulation, and we observed a stockout in 90 of them. So the MLE is 0.09 here, 9% chance. We know that that's just a guess. We have a formula based on what we just discussed in Unit 3 about how far off that guess might be. We can convert that into a 95% confidence interval. That's what we had just covered here. Here's actually another way to come up with the exact same answers here. So one thing that we know is that if we were to write out the probability of observing exactly 90 stockouts in 1,000 different trials, well, we actually know what that formula is. This is a binomial distribution, counting up the number of successes, stockouts, out of a fixed number of trials, 1,000 in this case. And if we go up and look and see, well, what is the formula for the PMF of a binomial distribution, this is what we end up seeing. The probability of observing exactly 90 stockouts out of 1,000 different Monte Carlo simulations here is 1,000 choose 90. That's a shorthand for 1,000 factorial over 90 factorial times 910 factorial times p raised to the 90 times 1 minus p raised to the 910 power. Based on the value of p, this is the probability of observing 90 stockouts out of 1,000 trials. And I want to focus in on what this likelihood looks like. So if I were to go and plot what this likelihood was versus p, this quantity that I'm trying to estimate, this is what the curve for the likelihood looks like. So p can be anywhere between 0 and 1 here. As I vary the value of p, the likelihood of observing my data varies. So really, really big value of p, very unlikely to observe that small number of stockouts. Really tiny value for p, also very unlikely to observe exactly 90 stockouts. The likelihood peaks right around that 9% here. That's what it meant to take the maximum likelihood estimate as 9%. That's exactly where the likelihood peaks. But we see that there are values that are near 9% that aren't that much less likely than if p was equal to exactly 9%. Let me zoom in on the likelihood. Let's look at values of p, say between 6% and 12%. So 9% is exactly where that likelihood peaks, but I could have chosen a value a little bit below 9%, a little bit above 9%, and that likelihood wouldn't have been really all that much smaller. Why don't I do something kind of similar to what I did when I was looking at the normal curve to describe how far off p hat might be from the true value of p, to quantify how much leeway I would have in my choice of p based on the appearance of this likelihood function. So this kind of looks like a normal curve. It's not exactly a normal curve. There's a little bit of a skew off towards the right. But why don't I do something similar and say, well, all right, taking P, our best guess, to be right at the peak makes sense, but there's a little bit of leeway. Why don't I give that leeway as the distance between this peak and where the inflection points are of the likelihood function? So essentially where the likelihood goes from going down faster and faster to kind of sloping out, this inflection point here on the left, and also the inflection point here on the right. How far is it from the peak to that inflection point? Maybe, any choice of p inside that range is, kind of plausible for what p might be based on the data that I've collected. Let's really pursue that idea. So how do I figure out, mathematically at least, where this inflection point occurs? Well, mathematically, it's actually where the second derivative of the likelihood function equals 0. So what do I mean by second derivative? Well, let's look at this curve, a different curve than what we were looking at for the likelihood. Here we see this curve reaches a peak, it goes down, it's sloping down faster and faster, then it starts sloping out. It reaches another point where there is a minimum right here before kind of turning over. When we were doing maximum likelihood estimation, we were trying to find the peaks of a curve, or the mode of a distribution. We were trying to find the peaks of the curve. If we look at the first derivative here, basically the slope of the tangent line, well, what we see is that just to the left of the peak, we have a slightly positive slope. Let me zoom in a little bit here. Slightly positive slope, and so a slightly positive first derivative, a little bit above 0 here. But very quickly, we reach the overall peak of that curve. We see there's a point where the slope of that tangent line is equal to 0, at least momentarily. And so that's where kind of the running tally of what that first derivative is crosses 0 here. This red line where the slope is exactly equal to 0, the first derivative is equal to 0, is exactly where this red line is right here. Now, as we move beyond the peak, what we see is that the slope is now negative. It becomes more and more negative as that slope gets steeper and steeper and steeper. And then all of a sudden we reach that inflection point, and while the slope is still negative, it's starting to kind of taper out. The slope is getting slightly less and less negative until, at least at this very kind of momentary minimum right here, the slope returns to 0 before turning positive again. And so we can see that in this curve. After the peak, the slope is negative. The slope gets increasingly more and more negative as we're heading down that hill until that inflection point. This blue line right here matches up with this blue line. This is where the curve goes from sloping down to sloping out. And that's where we see actually where the second derivative reaches a minimum here. So after that blue line, well, the slope is still negative, but it's decreasing, it's getting closer to 0, like what we have here. And once again, the slope becomes exactly 0 at this red vertical line right here, and that's where that minimum is going to be. So to find this inflection point, we actually need to look, well, what does the curve describing the first derivative looks like, and where does that reach a minimum? That kind of tells us where the nature of that curve turns over from sloping down faster to sloping out, and that's exactly the point that we want. If I look at the curve for the second derivative now, the derivative of this first derivative here, that actually equals 0 exactly where that blue line occurs. So mathematically, at least, this is a pretty well-defined problem. If I have the likelihood and I know where the peak is, and I want to give myself a little bit of a leeway as to what other values for that unknown parameter seem to be relatively plausible based on the data that I've collected, I can use that inflection point as a reference point for, where my level of reasonableness kind of includes values and starts excluding values. In fact, we could maybe use this distance as our measure of the standard error of our unknown quantity. So let's go with that. We're not going to use the math that we've learned in calculus to actually figure out where that second derivative is equal to 0. We'll use Wolfram alpha. So Wolfram alpha allows us to do second derivatives, the derivative of our likelihood. So omitting that choose function at the beginning, the Derivatives are going to be the same regardless. Let's ask Wolfram alpha for what the derivative of x to the 90 times 1 minus x to the 910 power is. We get a pretty long equation out, so we just ask Wolfram alpha, okay, well, where does this equation equal to 0? What value of x solves this equation? Wolfram alpha, a champ at solving polynomial equations, very high power polynomial equations here. But we get 4 solutions: x equals 0, x equal to 1, and then 2 kind of crazy looking expressions. Okay, well, we know 0 and 1 isn't the right answers because we observed some number of stockouts. Not everyone was a stockout, not everyone wasn't a stockout, so the answers aren't 0 and 1 here. So these must be the locations of our 2 inflection points. Notice this looks like a 0.09 or MLE minus something. And in fact, if we go and evaluate the second expression, this 999 plus the square root of 10, 10, 1 divided by 11100, this kind of looks like a 0.09 plus something. And in fact, if we take 0.09 minus this value that popped out from before, we get a value of 0.08. If we look to see, well, what's the difference between that other inflection point and 0.09, it's the same value as well, about 0.009 here. So here's our peak of the likelihood at 0.09, and it looks like this inflection point to the left or to the right occurs just about 0.009 away from the peak. So what if we use that as our numerical estimate of the standard error? Kind of a little bit of a buffer, a little bit of leeway associated with our MLE estimate. How does that compare with what we've been doing all along? You know, if we plugged in p hat of 0.09 into our formula for the standard error, well, we get a value of 0.00905. And isn't that kind of a funny coincidence? If I look at the distance from the peak of the likelihood to where that inflection point is, I also get a value of 0.00905. And so at this point, we might think, hey, we're kind of onto something here. Are these two things the exact same quantity? And the answer actually is, yeah, they kind of are. So if we actually want to know what is the standard error of our MLE, how far off might we think our MLE is from the truth? Well, since we had to get the MLE anyway from writing out the likelihood function, all we need to do is just kind of look at that likelihood function and see where the inflection points are. The MLE estimate is exactly where this curve peaks, where the likelihood peaks. And if we just say, all right, well, let's use as our standard error, kind of how far off our best guess might be from the truth, as the distance between that peak and this inflection point, well, this gives us a way to really figure out what that standard error is going to be for any probability model that we can come up with. Graph the likelihood function. We got to maximize it anyway to get the MLE, so let's just study it a little bit more closely and figure out, well, where's that inflection point? That distance between the inflection point and the peak is actually what we've been basically doing all along for our standard error of p hat, and the analysis is exactly analogous here for any probability model that we can come up with. So that's really our upshot. It turns out that for large samples, really more than a few dozen here, the standard error of our MLE estimate, the standard error of theta hat here, is just basically this distance from the peak of the likelihood to the inflection point. When we're dealing with a large enough sample, this is always going to be the case. And so this is what fitdist is actually doing here. Fitdist, which we've already learned, we know how to estimate the MLEs from the data itself. We already get a standard error actually from it when we print out a summary of fitdist. This is what fitdist is doing. Fitdist noticed that, hey, we could use as our measure for the standard error the distance between that inflection point and the peak. And the numerical method behind fitdist does exactly that. It's going and searching what is going to be the right value for that unknown parameter, find the peak, and along the way, it's keeping track of where that inflection point is. And we're going to use that distance from the peak to the inflection point as our measure of the standard error, how far off we think our guess, the MLE, might be from the truth, to complete our analysis. So from fitdist, we're going to get that standard error. We're just going to read it off. That's going to be the distance from the peak to that inflection point of the likelihood. How do we interpret it? Well, we know that our best guess, our MLE, isn't going to equal the truth. It's not going to be theta exactly. We're going to be wrong by some amount. The standard error is our best guess for how wrong we actually are. So we can interpret it in a couple of ways. We can say that our MLE is likely off from the truth by a standard error or so. Or we could say something like, well, based on the data we've collected, we estimate theta to be the MLE, give or take one standard error or so. And here's kind of the crazy thing about it. We can take this a step further and immediately come up with a 95% confidence interval, doing the exact same thing that we did when we were coming up with a 95% confidence interval for P. The MLE has this miraculous and amazing property that even though we only observe one MLE based on the data that we've collected, if we were to go and say run that experiment again or kind of run a simulation to say, well, if the data turned out a little bit differently, what's the distribution of the possible MLEs that I might measure? The MLE has this amazing property that we can anticipate how far off those possible MLEs might be from one possible sample to another. And it turns out that this distribution is once again well described by a normal curve. So we're immediately going to be able to say, okay, well, I've measured my MLE. I read it off of fitdist. I've measured my standard error, the distance between the peak of that likelihood and where that inflection point is. Basically a normal curve here. The possible theta hats I might measure when I go and collect data, not going to be exactly equal to theta, but probably off by a standard error or so. The distribution of which, the distribution of my errors, is well described by a normal. So a 95% confidence interval is just my theta hat plus or minus 2 standard errors. Just like what I did for coming up with a 95% confidence interval for P, and just like what I can do before, if I want a different level of confidence, I can use the relevant quantile of the normal distribution. And so that's it. That's the theory that's kind of filling us all with the ability to come up with not only a great guess for what that unknown parameter is for the probability distribution that's making our data, but then also a way to quantify the standard error, how far off we think our guess might be, and to leverage both of those to come up with a 95% confidence interval for that unknown parameter based on the data that we've collected. Now, before going on to a few concrete examples, I want to talk very briefly about the alternative way that people actually tackle probability problems and inference problems, this Bayesian method for doing inference. So back in Unit 1, we took the frequentist view of how probability is defined. We said that, okay, the probability of an event is the long-run fraction of time that we observe that event occurring. So it's an empirical definition. It's based on things actually happening. This alternative way of actually defining probability, quantifying uncertainties, is called the Bayesian framework. And in fact, we've seen a little bit of it with Bayes' theorem, conditional probabilities here. And Bayes' theorem actually provides kind of a cool way to do this inference, kind of building off on the stuff that we've already discussed, but kind of viewing the whole world on a slightly different angle. So, how does the Bayesian framework differ from what we've been doing all along? Well, in the Bayesian framework of probability, it takes it that the data values that we're collecting are actually fixed values and non-random. So the frequentist notion said, okay, every time we run an experiment, we're going to measure something different. What we measure is actually a random outcome. And the Bayesian framework does the opposite. The Bayesian framework says, okay, well, the data values are fixed. You have observed them. Every time you go and check to see what you measured, it's going to be the same quantity. There's no variation to that. So the Bayesian framework says the data values are fixed. It's that P, say the probability of observing any particular outcome, that's what's random. That's going to change from one trial to another. And so it's just the opposite framework. The frequentist definition says P is a fixed value. It's the data we're collecting, it's random. The Bayesian framework says, no, the data values are fixed. That's what we've observed. It's P that's the random quantity. It can vary from one value to another as we go from trial to a trial. And so here's how Bayesian inference actually proceeds. So Bayesian inference says, okay, well, that likelihood that we just plotted here, back when we were looking at where this formula for the standard error occurs, this likelihood, why don't we treat this as a PDF for that unknown value of p? The Bayesian framework says p is not a fixed quantity, it's random, it's the data that's fixed. And so this, looks like a great shape that describes a probability distribution. Why don't we use this likelihood as the basis for a PDF describing what p might be? Some trials p might be relatively small, some trials p might be relatively large. Why don't we use this as a probability distribution on p itself and see where that takes us? And so that's what the Bayesian framework does. So there's a little bit more to this story here that I'm glossing over. So if we take kind of a non-informative prior on p, the Bayesian framework actually lets you input in values of p that you think are more likely or not. But if we just say no idea what p is, any value between 0 and 1 on a trial-to-trial basis, then what we have is a formula for the shape of the PDF that we'd like. And we know how to convert shapes into actual PDFs. This isn't a valid PDF because if we were to integrate this formula from 0 to 1 here over the possible values of p, we don't get a value of 1. We get a value of 0.000999. But it's easy to convert that into a valid PDF just by taking the formula for the shape and dividing it by the area that we have right now. So 1 over this value turns out to be 1001 exactly. And so the Bayesian framework would say, okay, based on the data that you've collected, exactly 90 stockouts out of 1,000 trial, here's a probability distribution for this unknown value of p, this random quantity of p here. And we can confirm that's a valid PDF here. If I integrate this formula, it integrates to 1. And so that's what the Bayesian framework is going to allow us to do. The data, we've collected it. It's fixed. It's not random anymore. Every time we check its values, it's the same thing. It's the same sample we've collected. It's p that we're going to treat as the random quantity. And so why don't we do something like what we did back in Unit 5 when we were dealing with continuous distributions? Why don't I just come up with a 95% confidence interval by asking, okay, well, can I come up with a lower value of p and an upper value of p so that 95% of the area underneath this PDF is covered by that? Sure, we can do that. Why don't we just take the value of 0.073 as our lower limit of p, our upper limit to be 0.109. Why don't we use that as our confidence interval? How much area is between these two values here? Well, it works out to be 95.3%. And so if we did that, if based on this probability distribution, we took those two endpoints, then we could say that there's a 95% chance that p is between 0.073 and 0.109. If I wanted to be a little bit more careful and say get a 95% confidence interval for p exactly, I could just get the 0.025 quantile of this distribution, the 0.975 quantile of this distribution, and those would be my lower and upper limits. And kind of the cool thing is, if I do this the Bayesian way, all of a sudden I can say things that were forbidden with the frequentist framework. If I come up with this 93 or 95.3% confidence interval for p here, 7.3 to 10.9%, in the Bayesian framework, I can actually say that there is a 95% chance that p is between those two values. In the frequentist notion, I couldn't do that. P is a fixed quantity. I just don't know what it is. I don't use probability to quantify my ignorance about reality. But the Bayesian framework flips this whole thing on its side. P now is a random quantity, so it's okay to talk about the probability that it's between two different values. So if you're a Bayesian, it's perfectly acceptable to say, all right, based on the data that I've collected, there's a 95.3% chance that P is between 7.3% and 10.9%. So the Bayesian framework is actually pretty cool. You see it a lot in the natural sciences where you actually have a pretty good idea of maybe what that unknown parameter is ahead of time based on pilot studies, based on other researchers' work, and the Bayesian framework allows you to incorporate that prior information when updating your best guess for what unknown parameters are. We use Bayes' theorem to condition on information that we knew about the world to come up with a better estimate of the probability. Same sort of an idea here. So let's do some examples of coming up with standard errors, coming up with confidence intervals, and you'll really like this. It's a really easy procedure to implement because we're just going to do all of this numerically. So back to the hard drive example, we assumed that the time to failure of hard drives was exponential. We just didn't know what the value of lambda was. So we took some data. We said, okay, 150 observations, here's what we've measured. The MLE told us to take the reciprocal of the sample average as our best guess for what that value of lambda was. Turns out to be 0.2266. If we run it into fitdist, we say that, okay, well, that guess of 0.22666 is probably off from the truth by about 0.185 or so. And so we can make a 95% confidence interval just by doing plus or minus 2 standard errors. So if I take that 0.2266 plus or minus 2 standard errors, I could say that I'm 95% confident that lambda in this case is between 0.19 and 0.26. And that pretty much captures all the uncertainty that I have in this situation. Now, since we just talked about the likelihood method, just to show you that the value for the standard error really pops out to be this just from looking at the likelihood itself, well, let's write out the likelihood for this example. The likelihood for the exponential distribution, we essentially take the formula for the PDF, multiply it by itself n different times, go back and replace x by x1, x2, x3, etc. So we'd have lambda multiplied by itself n times. That's going to be a lambda to the n. We're going to have an e raised to the sum of all those powers, so minus lambda 1, minus lambda 2, minus lambda 3, etc., etc. Taking out that common value of lambda from each of those terms, we would eventually get to e to the minus lambda times the sum of all the x's. So in our data, we observed n was 150 observations. The sum of all the observations was 661.78. So the formula for our likelihood right here is as shown. So plotting that over an appropriate range of lambda, well, the maximum likelihood finds that the peak is right at that 0.2266. If we give ourselves a little bit of leeway and say, okay, well, let's take as our standard error how far off we think we might be from the truth, these other values of lambda that aren't all that much less likely here, we would get an inflection point here, and that is what fitdist is reporting back to us. We can use Wolfram alpha to actually figure out, well, where is the second derivative of the likelihood equal to 0? That's letting us know where those inflection points occur at about 0.208, boom, right there, and at about 2.245, right there. If we look at the difference between where those two inflection points occur and where the MLE is, 1 over the mean of those observations, we get that 0.0185. So MLE, give or take this number, and you'll notice that's the exact same number that fitdist is reporting back to us. So it's one and the same. That's where fitdist is getting its number from. It's just looking at the likelihood, it's checking out its curves, it's studying it very, very well, and it's finding that inflection point where the likelihood goes from sloping down faster and faster to sloping outwards. So if we really wanted to, dive deep into this and, not say, hey, Wolfram Alpha, save us, there are some formulas that you can actually go through and derive analytically what does the standard error equal to, based on the sample size, based on the data that's been collected. And this is just here for completion. This is not something that you would do as an undergraduate unless you're in a pretty advanced mathematics class. Even in Bayesian 533, the class I teach for the master's program, where we do dive pretty deep into the math, we only briefly touch upon the mathematical procedure for coming up with a formula to get that standard error. It's fairly complicated. If you love math, it's really cool to actually go through this and be like, wow, I can sit down, just do a little bit of calculus and figure out what the formula is for the standard error. But if you're not into math, this really is kind of lost on you. Just to connect it with what we're doing, we're modeling the standard or modeling the failure times of these hard drives by an exponential distribution. The MLE says take the reciprocal of the sample average. In this case, there's actually a formula that tells us how far off that best guess is going to be. The standard error of lambda hat in this case turns out to be the square root of 1 over the sample size times the square of the sample average. Who knew? There's actually a formula for it. Fitdist gives us a number on a case-by-case basis. For most of us in BAS 471, that's good enough. We just want to number out. Bayesian 533, we're a little bit more interested in studying the general trends. It's kind of cool that we can get a formula for that. But the answer turns out to be exactly as expected. There's multiple ways there. And that formula, that square root of p hat, 1 minus p hat over the square root of n, we discovered that formula through a very carefully constructed set of investigations back in Unit 3. But that's really where this formula comes from. You go and sit down and say, okay, I'm going to mathematically derive the formula for the standard error. It takes a lot of derivatives. It takes a lot of algebra. But when you go through that algebra, when you go through the math, that's also the formula that pops out. So we discovered it with a very careful set of observations, but mathematically it's very well grounded as well. So we know how to get the standard error. That last remaining question is, how do we get the confidence interval? So here are the two key properties of the MLE. This is why we love the MLE so much here. For large sample sizes, number one, we know the MLE is almost unbiased. Might be for any particular sample a little bit too high, a little bit too low in reference to theta. But on average, it gets it just right for large samples. And of all unbiased estimators, it's going to be the one that typically gets closest to the truth. But here's what I like even more about it. For larger sample sizes, the possible values that we might measure for the MLE when we go and collect data has a well-known distribution. It might be a little bit above, it might be a little bit below. We, on average, land right on the money here. But the distribution of how wrong our MLE is very well described by a normal distribution. And so we can use the properties of the normal distribution that we've been doing all before to come up with that confidence interval. We know that with the normal distribution, there's a 68% chance of getting a value that's within 1 standard deviation of the peak. So there's a 68% chance of observing an MLE that's within 1 standard error of theta. Likewise, with a normal distribution, there's a 95% chance of observing a value that's within 2 standard deviations of the peak. So there's a 95% chance that we'd observe an MLE within 2 standard errors of theta here. So what we do is we take our 1 MLE and then go plus or minus 2 standard errors away to get that confidence interval. If we want to be a little bit more careful about it, if we want a different level of confidence, we can just appeal to the quantiles of the normal distribution. And so we have our master formula for the 95% confidence interval or any other level of confidence. The MLE, we'll read that off of fitdist. The standard error, we'll read that off of fitdist. All confidence intervals are just the MLE plus or minus some number of standard errors. That number is given to us by the relevant quantile of the normal distribution. For 95% confidence, it's basically 2. For 99.9% confidence, it would be plus or minus 3.3 standard errors. So there we go. Doing estimation with the MLE is really quite nice. We can come up with a best guess for the unknown parameter theta. We can get a pretty good idea of how wrong we are, the standard error, and we can leverage those into coming up with a 95% confidence interval. So when does this procedure work? Well, number one, we need to make sure that we have a large enough sample size. So when the sample size is large, more than just, a couple dozen or so here, we require more than about 25 or so data points, we're good to go. We'll be able to use this procedure to come up with the confidence interval. Number two, it can't be one of those weird distributions where the possible values of x depend on that unknown parameter theta. So we've talked about MLE estimation for those cases, and it gets tricky. We have to use logic to actually solve the problem. If we were dealing with a case like the values of x's are uniformly distributed between 0 and some unknown upper bound, because the possible values of x depend on theta here, we have that interplay. It actually breaks down our whole, using calculus, numerical methods for coming up with that MLE. It turns out it's the maximum value of x in this case. The confidence interval approach is also going to fail as well. So if we can't get the MLE numerically, this is going to fail as well, just for those corner cases. But that's really our main summary. This works most of the time, and that's what people use time and time again. Tying it back to our COVID-19 simulator, well, we had some data kind of probing what the initial spread of the outbreak looks like through a bunch of different cities, kind of frozen, snapshotted on a particular set of days from 9 to 20 or so after the outbreak. if we fit our probability model that describes this curve, what we found was a MLE for where this tapering off point was of about 0.755. If we studied the likelihood a little bit more carefully and said, well, where's that inflection point? The inflection point for that leveling off point turned out to be about 0.1 away from the peak. So we leveraged that, we combined it, and we said, well, we're 95% confident based on this data, based on our disease spreading model, that eventually 75.5%, give or take 20 percentage points, 2 standard errors, will become infected with the disease here. All right, so the rest of the slides here just go through some additional worked examples. What I want you to concentrate on for BAS 471 is just the numerical way. Do fitdist, get that MLE, get the standard error, make a confidence interval. How does that work for a few of these examples here? Well, let's review. So let's imagine that we're dealing with a distribution that we think is making our data. I'll name it the Jackson distribution. I don't know if you can hear him snoring. I'm wearing my headset, but he is snoring up something fierce right now. And so in his honor, let's say that this is named the Jackson distribution. It's right skewed, like everything in analytics. It has one peak. The location of that peak, the size of the skew, is all controlled by this unknown parameter theta. So let's imagine that we have a random sample and we want to come up with a 95% confidence interval for theta. So I'm going to skip the math way. If this interests you, knock yourself out. You can actually come up with a formula for how far off you think the MLE might be. We're just going to worry about how do we get this quickly with fitdist. All right, so since this is a custom distribution, we need to define the D function. So dcustom left arrow function x comma theta. We only have one unknown parameter theta here. And all we have to do is transcribe the formula for the PDF based on x based on theta. So I've done that here. And then what I do is once I've collected my data, I'm going to name that into a vector called observations and then run fitdist. Fitdist observations, custom in quotes, whatever I've named it here, and then giving it a starting guess. So start list theta equals 5, why not? It's not sensitive to what my starting guess is. I could try different values. I would get 5 back each time. But fitdist says, okay, well, it looks like the location of where the likelihood peaks is right at about 6.6 here. So our best guess based on the data that's been collected is that theta is equal to 6.6. We have a value for the standard error. We think that, okay, we're wrong, that 6.6 is wrong, but it's not that wrong. We're probably off by about 1.3 or so. And so we can make a confidence interval just by taking the MLE, give or take 2 standard errors. And so we can say that we're 95% confident that the true value of theta, of the Jackson distribution that's making our data here, is somewhere between about 4.0 and 9.2. So not too bad. Let's do another example. Poisson distribution. That's a member of the notorious family that we've worked with a lot. So how would this work with fitdist? All right, well, let's make some data here. Let's just make some observations, and then we'll run the fitdist command. So since it's notorious distribution, I can refer to it directly just by saying, all right, fitdist observations, my observations vector, and then Poisson in quotes. Left arrow it to fit, get a summary, and here we go. Based on the data that I've collected, my best guess, the MLE for lambda, is 5.25. That happens to be the sample average. I know that's wrong. How wrong am I? Well, I think that this guess of 5.25 is probably off by about 0.41 or so. So 95% confidence interval, take the MLE, give or take 2 plus or minus 2 standard errors. We're 95% confident that lambda is somewhere between 4.4 and 6.1 here. So not too bad. More math, if that's your cup of tea. And then finally, this modification to the Poisson example. A lot of times we want to model something with a Poisson, but 0 is not really a valid quantity. 0 is okay if we're dealing with the Poisson distribution. If we're modeling the number of items, say people have in their cart at checkout, 0 is no longer a viable option. So we have this 0 truncated Poisson. The formula for the PMF looks like this. The possible values of x are 1, 2, 3, etc. What if I have some data here? So here are 2 lines that creates a random sample from this distribution. Here's a summary of my observations. The average is about 2.55, minimum of 1, maximum of 7. If I want to model this distribution with a zero truncated Poisson, well, what's going to be my best guess for lambda here? All right, so I got my data vector. I'm going to use fitdist to get my answer. It's a custom distribution, so I'll define dcustom as my function with x and lambda, this one unknown parameter, and then I'll simply transcribe the formula for my PMF. So I just got to be very careful to transcribe that correctly. But once I have that done, it's easy. Fitdist, the name of my data vector, custom in quotes, or whatever I've named it here, and then a starting guess. So start list lambda, how I've defined this PMF here, lambda equals 7. Just some sort of random starting guess. This isn't sensitive to the value that I've chosen here. If I were to change this up, I'd get the same MLE no matter what, pretty much. And so fitdist is saying, all right, well, your best guess for lambda in this case is right at about 2.3. You're wrong, of course. How wrong are you? Well, that value of 2.3 is probably off from the truth by about 0.2 or so. So 95% confidence interval for lambda, lambda hat plus or minus 2 standard errors, 2.29 plus or minus 2 times the value of that standard error. And there we go. So once we've kind of become familiar with that maximum likelihood framework, moving beyond just a guess for what that unknown parameter is, to coming up with a standard error, how far off we think that guess might be, and then going even a step farther and coming up with a confidence interval for that unknown parameter really isn't all that bad. We can do it all in fitdist, and so hopefully you'll have a relatively easy time on your next set of problems. So that's it for today. Good luck.